We now come to a description of hadronic showers. We saw that electrons, they lose their energy mainly through ionization, and photons, they interact and they change their identity by changing into an E plus E minus pair. And for hadronic showers, which are the result of an energetic hadron traversing matter, you get a combination of the same effect. So the hadron, if it's charged, it will ionize the material, and this will give rise to an electromagnetic shower. And it will also then interact through the nuclear interactions with the atoms in the material. And in that way, it will change its identity. It will completely change, for example, from one proton into several protons plus neutrons. So in nuclear collisions, we have secondary particles, and these particles, they can decay electromagnetically. The lightest meson is a pion, and these are abundantly produced. These things immediately decay into two photons and produce electromagnetic showers. But the secondary particles can undergo secondary collisions and also tertiary collisions. And so this will give rise to a hadronic cascade. So hadronic showers have electromagnetic component and hadronic component. The difference between electromagnetic and hadronic showers is the shower development is very similar, but hadronic showers are much more complex. They're governed by the strong interactions. There's a much larger variety of processes, and there's a fraction of dissipated energy which is required to break up the nuclei that is undetectable. And the scales of the hadronic and electromagnetic showers are determined by the differences between the cross-sections for nuclear and electromagnetic interactions. If we look at the nuclear interaction length, lambda int, this is the average distance that a high-energy hadron has to travel before a nuclear interaction occurs. So very much like the mean free path. So using that concept, you can calculate the probability to traverse a distance z through a material without a nuclear interaction. And it's given there, it's the exponential of minus z divided by the interaction length. The cross-section for nuclear interactions is inversely proportional in the same way that we had for photons with the mean free path. Turns out that the interaction length is proportional to the atomic mass to the power 1/3. In heavy materials, this would be about 10 centimeters. And you have to note that for pions colliding with matter, the cross-section is much smaller than for protons, because pions are smaller, they have a much smaller size. And so this means that the interaction length of pions is longer than that for protons. Pions travel up to 25 to 50% longer than protons, and the shower will start later. In addition, there's baryon number conservation. A proton hitting a nucleus will have, because of baryon number conservation, the primary secondary particles coming out must also be baryons, and these will have again shorter mean free paths. So hadronic showers from pions are longer than those for protons. Here you see the material properties for various materials. For protons, you can see that the interaction length is much longer than the radiation length. So you need more material to contain hadronic showers than electromagnetic showers. On this plot you see the longitudinal profile. Looks very similar to electromagnetic profiles. You need about 8 interaction lengths of uranium to contain 95% of the hadronic showers of the 300 GeV pion beam. However, 300 GeV electrons would only require 10 centimeters of uranium. The lateral profiles, they have a different kind of shape. You see in the center there's a narrow core. This comes from the electromagnetic showers, from the pi zeros, and then there's a decreasing halo from the non-electromagnetic component. And a cylinder within 1.5 interaction lengths of material contains 95% of the showers. And again, this is much larger than for electromagnetic showers. Now we can look at the proportion of these hadronic showers that will end up decaying electromagnetically. If you assume that 1/3 of the mesons that are produced in the first interaction are pi zeros, then these will decay into 2 photons and give an electromagnetic shower. Then in the second interaction, again, there will be the same fraction of pi zeros, and so we get a power load. Every collision we have 1 minus 1/3 of the remaining energy is available, and so as a function of the energy of the incoming hadron, the fraction would be 1 minus 1/3 to the power n, where n is proportional to the energy of the particle coming into the shower. The reality is a bit more complicated. We don't only have pi zeros, so 1/3 is an upper limit, and there are other effects which mean that this number n is not completely proportional to the energy. And it turns out that there's a formula that describes it better, which is 1 minus E divided by E0 to the power k minus 1. And here E0 is the average energy to produce 1 pion, whereas E is the total energy of the incoming particle. K minus 1 is related to the average multiplicity, so the number of mesons that are, or hadrons that are made in the collision. It's approximately 5. And then the average fraction of pi zero production, which is less than 1/3. And these are all linked through the formula that I've written there. K equals 1 plus log of 1 minus fp0 divided by the log of the average multiplicity. It turns out that K is pretty much independent of the material. It's approximately 0.82, can be a bit less. But E0 depends much on the material. If there are more protons around, then it will be the E0 will be higher. The amount of energy required to make a pi zero is higher in a heavy material. And these things have been experimentally verified. You can see in the plot, the continuous line is for lead, the dashed line is for copper, and the measured points, they follow pretty much the formula at the top of the page. Of course, the fraction of electromagnetic showers for protons is 15% less than for pions because of baryon number conservation. There's less energy for pi zero production, and it is the pi zeros that generate these electromagnetic showers. Then the secondary hadrons, which are charged, if they're charged, they will radiate and they will have ionization losses because the interaction length is quite long, and so they will lose. So typically protons will lose between 150 and 225 MeV, I think this table was for 100 GeV protons. And then pions, they travel longer, so they lose 25% more energy. Yeah, this is for minimum ionizing protons, in fact. So it's not the incoming proton that is important. Using this, the slide on the previous, on slide 40, the formula for magnetic component, we can work out particle multiplicity. So if you take an example of 100 GeV pions on copper, the electromagnetic fraction is about 60%. And that means that for per pion, there will be 40 GeV left for hadronic interactions, and dividing that by E0 of 0.7, you get to 58. So there will be 58 hadrons produced in the non-electromagnetic component. And the number of pi zeros will be then 1 divided by 1 f pi 0 minus 1, which is approximately 1/3 of the total number of hadrons. And you can then see that for this particular case, if you look at the table at 100 GeV, that is 19 pi zeros. These all, so the hadron loses ionization energy, which is 15% of the initial energy, and 65% of the non-electromagnetic energy is used to excite and dissociate atomic nuclei in the absorber. We'll come back to that a little later. We can estimate the number of generations, and that would be approximately 3. And you have to realize, so the energy dependence of this electromagnetic fraction, which was calculated in this table, has important limitations on hadronic energy resolution, because the hadronic part contains a large unmeasurable part of energy that is lost due to recoil and binding energy. So if we look at what happens inside the nucleus, the nuclear sector, we have spallation interactions. And spallation occurs when a high energy hadron hits an atomic nucleus. And then there's ejection of material from the target during the impact by the projectile. That is what is a spall. Now there are two phases. There's a fast intranuclear cascade, which happens in 10 to the minus 22 seconds, followed by a slower evaporation stage where particles are ejected from the nucleus. So in the fast stage we have quasi-free nucleons which collide with other nucleons. Pions and other hadrons may be created, and some of these particles that have enough energy to escape the binding energy, they can go out of the nucleus and they can continue their path in the material. And the rest will receive the kinetic energy that is left over from the incoming particle. And this will then also, when these particles leave the nucleus, give rise to further secondary reactions. In the slow phase, we have the intermediate nucleus that de-excites, and the free nucleons are evaporated, either as alpha particles or heavier nucleons, or as nucleons, neutrons and protons. And the energy that's needed to release these nucleons is lost for calorimetric purposes. This is about 30 to 40% of the non-electromagnetic shower energy altogether. Now, the large event-to-event fluctuations in visible energy, they will account to a worse energy resolution for hadronic calorimeters. If you compare it to the electromagnetic resolution. Cascade particles, they have a momentum component along the direction of the incoming particle, and so the residual target nucleus undergoes a recoil. This amounts to about the proportion of the total mass of the cascade nucleons divided by the mass of the residual nucleus. And this is not measurable, it's part of the invisible component of the shower energy. Then the evaporation neutrons, they're emitted isotropically. Now we can estimate the average number of protons and neutrons. We can estimate also the invisible energy, and we can separate the cascade nucleons from the evaporation nucleons. And to do this, there's an empiric formula from a chap called Rudstam, and he calculated the cross-section for all the possible final state atoms that you can create when a certain atom is hit by an energetic particle. And so there are many, so the heavier the target atom, the more possible final state atoms there are. And for each individual final state atom, you can work out the cross-section using this formula. And if you then do that for a particular case, like in this case, we have a 1.3 GeV pion hitting lead, then 300 MeV is lost by ionization before the pion interacts with the nucleus when it goes through the material. And then you can work out all these different cross-sections, and from these cross-sections you can calculate, because you know the number of protons and neutrons you originally had in the lead atom, you can work out what the distribution will be as a probability of protons and neutrons. And for protons, we get approximately 2.7 protons and 12.8 neutrons. There are many more neutrons than protons. In total, there will be 16 spallation nucleons. Now, you can also look at the energy, the probability, given a certain energy of a proton and a neutron, whether there would be a probability of emission or not. And in fact, for an energy less than 200 MeV, as you can see on this plot, the probability of emitting a proton is negligible. Now we can work out what the energy is of the protons and the nucleons, and it's less than 200 MeV in this particular case. So all the protons that are made in the cascade step. Then there will be proportionally as many neutrons in that step, which would be 4.2 neutrons. So we have 7 nucleons made in the cascade step. And then there are 9 neutrons left, which are emitted in the evaporation step. So you can work out the nuclear binding energy, which is 7.9 in this particular atom, lead. And the 9 evaporation neutrons, they have very low kinetic energy because they're thermal neutrons, and that would be then approximately 2 TeV per nucleon, total 27. That means that there's 847 MeV left over to share between the target nucleus and the cascade nucleons. The recoil energy will be 30 MeV, And so we're left with 117 MeV per nucleon. And so you can see that for 117 MeV protons, they will not have further spallation interactions, and their range in lead would be 2 centimeters, whereas their nuclear interaction length is 17. So these protons will lose their energy by ionization, and the remaining 4.2 cascade neutrons will induce new spallation reactions. And it's one of the exercises for you to work out the energy distribution among the secondary nucleons which are created in the secondary reactions. If you work it out, then you can see in this table what the total binding energy is that would be lost, the number of evaporation neutrons, the ionization, and the target recoil energy that is lost. And so that will then give you an idea of how the energy is distributed in this particular reaction, and that has an impact, as I said before, on the resolution of your hadronic calorimeter. The evaporation neutrons, which are thermal neutrons, as said, with an energy of approximately 3 or 2 MeV, they will lose their energy through elastic neutron scattering. This happens for energies between a few electron volt and 1 MeV. The energy loss varies between 0 and this formula. For hydrogen, this would be 50%. That's why often hydrogen is used for shielding, and it has an impact clearly on the design of your calorimeter. Then there will be alpha particle production between 3 and 20 MeV, inelastic neutron scattering, and neutron capture when the neutrons have lost all their energy, and this will then transform the absorbing nucleus into a new type of nucleus. That terminates this part. Here's a quiz. If you don't know the answers, go back to the slides. Then finally, there's a summary here. So shower particles travel in random directions with respect to the particle that initiated the shower. This has an impact for the calorimeter design because the orientation of the active layers of a sampling calorimeter is therefore not important. You will see this in the lecture on calorimetry. Both electronic and hadronic showers, we have the major part of the energy carried by very soft particles. Electromagnetic showers, 40% of the energy is deposited by E plus E minus, with energy less than 1 MeV, 1/4 by positrons, 3/4 by electrons. They lose their energy by Compton scattering and photoelectrons. Typical particles in these showers are 1 MeV electrons with a range of less than 1 millimeter. Hadron showers, the typical particles are 50 to 100 MeV protons, 3 MeV evaporation neutrons. The range of 100 MeV proton is about 1 to 2 centimeters, neutrons several centimeters. They have different deposit energy mechanisms, and there are differences in the shower profiles that can be exploited to identify the particles that cause the signals. This concludes the lecture on electromagnetic and hadronic showers. Thank you for watching. Please, if you have any questions, send them to me by email so that we can discuss them next week. I'm sorry, I'm not as modern as the other lecturers who have an anonymous way of submitting questions. I promise that I will keep your name confidential. So don't be shy, ask any question to me by email. The more questions you send now, the better the reply will be that you get during next week's Zoom session. Also, I have here a set of problems that you can work on. You should be able to do them using the knowledge from the lecture. and we will go over the answers next week. Thank you, and we'll see you next week.